All right. Hi, this is Johnny. I decided to re-record this video because the first one, my webcam was really big and taking up a big portion of the screen. But yeah, essentially this video, I'm going to be going over the very first challenge in the demo that I created for ROP chaining, the ROP Trainer repo. And we're just going to be learning about a basic overflow attack, and how we can execute that. But before we can get into that demo, there is a bit of background information that we're going to need to know about buffer overflows, right? So at a high level, essentially what a buffer flow is it's going to have a setup like this. We're going to have some vulnerable function that takes in a user input. In this case, it's taking it from this file right here. It takes in a user input and then writes it to a buffer of fixed size right here. You can see we have a buffer of length 16, and we're going to have an input read into that buffer. And an important thing about these buffer overflow attacks is that they're going to occur when this input is unsanitized. And what that means in this case is that we're not actually checking how long the input is. So it's very possible that if a user writes an input that's more than 16 bytes, it's going to overflow from our buffer. So hence the name buffer overflow, right? So now we know, essentially, at a very high level, what a buffer overflow is, but why exactly is that dangerous, right? Like, why do we care if a user just happens to write a little too much to the buffer, right? How is that even going to affect our program? Why is this a malicious exploit? Well, to understand why this is so dangerous, we're going to need to know a little bit about the stack. So if you haven't seen this before, essentially, whenever you make a call to a function in your program, there's a region of memory called the stack that's used to store information about each of those function calls. Right, so you can see here, I've included a diagram of what it looks like in x86 assembly, specifically for 64-bit systems, because that's what most people will be working on these days. But yeah, essentially what gets stored on the stack, you have important things like the return address, arguments passed to the function, any local variables you've defined in the function. In this case, we have our buffer right there. And then another thing that we have here is something called the RVP. And what the RVP is it's just a register that holds the frame pointer. And the frame pointer is a value, or essentially like it's a reference point in memory on the stack that allows us to have a fixed reference point, or I guess frame of reference, so that we can access all these important values, like our return address, like our local variables, stuff like that. So yeah, this is providing us with a fixed frame of reference, and we'll be using that reference point later on in our exploit when we're needing to access, like specific memory addresses. So yeah, this is just a high level of what the stack is, how that works. If you've heard the term stack overflow before, maybe you've encountered it when you program like a recursive function that didn't terminate correctly, right? What's happening there is you're making a bunch of these function calls, and each of those function calls needs to store essentially this like metadata about that function call itself onto the stack. And then if you call that too many times, this eventually your stack is going to run out of space. And that's what's called a stack overflow, just distinct from buffer overflow, but yeah, just thought I'd put that in there. Anyways, let's see this in action. Let's say that we actually want to write something to this function right here. We put in hello world, typical standard input. What actually happens on the stack now is this value in hello world is going to get copied into the space that we have for our buffer. You can see here I've actually split the buffer up into two spaces in memory because, well, in a 64-bit system, each of those is going to be 8 bytes. So, I mean, if the buffer is 16 bytes, then it's going to take up 2 memory locations. And you'll note that the stack actually grows towards lower memory addresses right here, right? So the buffer, which is up here, would be based on the RBP minus 16 bytes. And then this address right here, which is the second half of the buffer, is going to be RBP minus 8 bytes. Just a bit of notation, so you guys are aware how that's going to work and like the offsets that we're going to be using to access certain values. So yeah, like I said, we write this hello world, it goes into the buffer, and this is what it looks like in memory. We have the first 8 bytes of that input, starting at the beginning address of the buffer, and then the last, I believe, 4 bytes of that input right here. This should be a +4. I need to correct that. I don't know why I haven't done that yet. But yeah, no issues here. We can see that, or well, I guess we'll note that hello world is only 12 bytes long, right? So it fits within the 16 bytes that we allocated. So, I mean, it fits nicely. Nothing happens, nothing breaks in our program. But what if our input wasn't so nice and convenient, right? What if it didn't actually fit within the space that we allocated for it? Well, let's say that we have some more malicious input, like So I love Bank of America so much. And, beyond how just inconceivable that statement is on its own, we'll also notice it is a lot longer than that previous message of hello world. It's actually exactly 32 bytes, if I've counted correctly this time, which we'll note, right, is more than the 16 bytes that we've allocated for it. So let's try and take a look and see what's going to happen in this case. So we can see that those first 16 bytes do get written to the buffer, but the remaining 16 bytes just keep getting written and they override our other important values that we have on the stack. So we're overriding that saved RBP or frame pointer, and then perhaps more worryingly, we're also overriding that return address. So if we think about what's going to happen after we've read in this input, when we try to return from the vulnerable function, it's going to see these characters that we have from the input string as the return address, and it's going to try to return to that point in the program. And most likely, that's going to be an invalid return address, and we're going to result in every C programmer's worst nightmare, a segfault. Right? So the program is going to crash here. So yeah, this is pretty much at a surface level why a buffer overflow is really dangerous. Like, first thing we can see here is you can overwrite the return address, which, one, it could cause a segfault, but if we want to be more malicious with it, this also means that we can change the direction of the program to essentially run any function we want, right? Because if we can control the return address, we can control how the program flow executes. And beyond that as well, I mean, you can imagine maybe if we had like another local variable below this buffer declaration, we could end up corrupting that value if we overwrite to the buffer and it just overflows into the space allocated for that other variable. And then, as we'll learn later on, this exploit can actually turn into a capability for arbitrary code execution. But returning for a second to that exploit I just talked about modifying the return address to redirect the flow of the program, it's exactly what we're going to do in our first demo. But before we're able to actually carry out that attack, we're going to need to learn a little bit more about one of the tools of the trade, and that's going to be GDB. So if you've ever programmed in C before, you're probably at least somewhat familiar with GDB, or at least what it does. But yeah, it's the debugger for C programs, and it lets you do a lot of really cool, useful things like stepping through a program, viewing memory addresses, the raw assembly for the C instructions, and then even reading register values and things like that. And some key commands that we're going to be using are disassemble, which will allow you to view raw assembly for an input C function. You can actually see the output right here, what that would look like. That vulnerable function that we had before, it breaks down those two small C instructions into a bunch of different assembly, right? So we can see what's actually going on at a lower level. Another important thing that we're going to be making use of is the fact that it actually also lists the addresses of each instruction. And a probably useful thing to note here is that the first address that comes out of this disassembly, we can essentially treat that as the starting address of that function. Whenever we make a call to that function, like what we have here, this address, the address that gets passed in there is most likely going to be just that first address that comes out. Another thing that's going to be useful is breakpoint, which I believe the command is actually just B, not breakpoint as a whole. But this will allow you to set breakpoints at certain memory addresses or instructions in your code, which can be very useful for testing purposes, and indeed it will be useful for our demo too, so we can check in on what's going on in the program flow. Last thing we're going to use are the X and print commands, and these will allow you to view values associated with memory addresses and labels respectively, so like variables or just raw memory addresses. I think we're going to be making more use of the X command, and there's a bit of nuance as to how the syntax for that works, but we'll get into that with the following demo. Speaking of which, we should know enough to get started with our first buffer overflow attack now. Just to set the scene, we're going to have that vulnerable file input from before. And our goal here is to redirect the flow of the program to go to this win function. So we want to print out the you won message, even though win itself is never called in our code. And a basic idea of what we're going to want to do here, we'll know earlier that when we wrote too much to that buffer, we eventually overrode that return address, right? Specifically, after we filled out that buffer, overrode the saved RBP, and then the next 8 bytes that we write will become the return address. And in this case, we want that to be the address of win. So I'm going to walk you guys through how we can carry out this exploit using a bit of setup from my repo with the demo that I created. So let me just set this up right here. So when you clone my repo, this is what you're going to see. I've created 3 challenges. This challenge 0 is the one we're going to do first. So you can just go ahead and navigate to this repo. Um, and then for these demos, I've also created Docker images because there are currently like a lot of modern protections in place that will protect against some of the attacks we're going to carry out in these demos that we're doing. So I've created a Docker image specifically with those protections turned off so that we're actually still able to carry out these attacks. All right, anyways, let's go ahead and set up that Docker image by running the setup script I have right here. It'll likely take a little bit longer if it's your first time setting it up, but I already have the image, so it doesn't take that long. All right. Actually, before we do that, I guess we should take a look at the code itself. So let me open up what we have in this repo. So we can see here, here's the program that we were talking about earlier, right? We have our vulnerable input and then the win function that we want to return to. And how we're going to feed an input into this vulnerable program right here, I've created a payload Python script. Oh, don't look at that. But essentially, this will allow us to write raw bytes to the output buffer, and then the build script I've had right here will compile that output into a readable binary for the C program that we're trying to attack. But before we get to actually constructing that input, let's take a bit of a look at what's actually going on behind the scenes in that vulnerable function right there. So if we go back into that Docker image, set up again, and now we try to run the build script. So what the build script does is it'll take your payload and convert it to a binary, and it'll also compile the ROP vol C file. I already have them compiled, so they're here already, but if you're doing that for the first time, that's what they're going to be doing. Then let's jump straight into it by using GDB to check in on what's going on in ROP vol. So remember, our goal here, we want to fill in the padding and then the address of win. So I guess our main goal here is going to be figuring out what the address of win is. But before we get straight to that part, let's go ahead and take a look at what the flow of the program is. So, it's going to start executing from main. You can see it's doing a lot of different stuff, and then it's calling the vulnerable function. We'll note that win isn't called anywhere here, right? So, we have to do the heavy lifting in terms of telling the program to go there. Otherwise, it's not going to do it on its own. Let's go ahead and look at vulnerable now. I included this in the screenshot earlier, but yeah, you can see it's moving some stuff in registers, and then it's calling that read input function right there. And finally, let's take a look at the win function. This is going to have some information that's going to be useful to us. You can see here, this is going to be that starting address for win that we want to use. So let's go ahead and see if we can try to create some sort of input that will get that into the return address space. But yeah, I guess before we jump straight into that exploit, let's try, or yeah, I guess let's just do it, but break it down into easy to digest steps. So the first thing we're going to need to write to our output is that padding, right? And we'll note that we'll need to fill out 16 bytes for the buffer and then another 8 bytes for the saved frame pointer that we have. So let's go ahead and try to write that first. And you're going to do that by just doing this, right? This is going to be the syntax that you can use to write raw bytes to the output. And I'm just going to use hex 41, which is a capital A. No particular reason, that's just the one I'm drawn to. So, okay, let's pause there and go ahead and build our output again. So now we should have our updated payload. And let's go ahead and open GDB again. And we want to see what it looks like when we run it with this input. So let's go ahead and set a breakpoint. First, let's set one right here before we read the input so we can see the state of the program, what it looks like then. And then let's set another one right after we read the input. And you can see here that I'm using that B command I talked about. If you're putting in a raw memory address like this, you're going to need to put the asterisk in front. There we go. We have 2 breakpoints set. And then to run the program with our payload, we can just do rs payload.bin. Okay, so we've reached our first breakpoint. Let's go ahead and check in on what values we have in memory currently. So first, that buffer should be located at our RBP minus 16, right? Because the buffer is 16 bytes, so it's going to start 16 bytes upward. And we can do that by just doing this command right here. Let's do x/1gx RBP minus 16. Yeah, okay. And so we can see here that right now there's just some arbitrary garbage values in the memory right now. Is this the right value actually? Hex 010. Yeah, yeah. Okay, so this is just going to be some garbage value in the buffer, which makes sense because we haven't written anything there yet. And then let's also check in on what the current return address is. It should be somewhere in main right now because that's where it's called from. And we'll see that it's this hex 401973. And if we disassemble main, we'll see that, yeah, that's actually this line right here, right after we call vulnerable. So looking good right now, nothing malicious at all. But let's go ahead and continue execution after we run our input and see what it looks like. So we hit our second breakpoint. Let's go ahead and check again on that buffer that we had. And now we can see we've filled it in with all these hex 41s, right? And if we did it correctly, it should now be filling up the entire buffer and also that RVP right there. So let's go ahead and change this from 1GX to 3GX. By the way, just to briefly talk about how the X command works, because I kind of glossed over it. This first number is the number of units that you want to read. The second number is essentially, I guess, the data type of the unit you want to read. So in this case, we have G, which I think it stands for giant word, but essentially what that means is just one entry in memory for us. So one of these rows in the stack that I have here. You can also use things like S. Actually, if I do x/1s RVP minus 16, you can see it'll read it as a string instead. So the hex 41 is interpreted as capital A's. But yeah, to go back into this command, so this will say, let's read one giant word, and then this last X right here is telling us to display it in hex, which is why it came out as hex 41 instead of something like just A. Okay, so now that that's taken care of, let's go ahead and do a x/3gx with RVP minus 16 as the start. So we can see, yeah, so these two right here are going to be our buffer, completely filled with the hex 41s, and then this is the RVP spot itself. So this part right here, also filled in with all those hex 41s that we put in. But then if we read the return address, it should still be the same. Yeah, this one's the same because we haven't filled in this part yet. So yeah, looks like our exploit is working so far. All we need to do is put in that address for win and see if we can get this fully functional. So let's go ahead and take this address right here that we got from the disassembly. And the way we can write these hex values to our buffer is going to be a little bit different from the padding that we did. We're going to have to do something like this. We do a 2 bytes, 8, oops, and then we want to specify this is going to be little endian. That's just because how x86 is going to expect it. And yeah, this should actually be our completed exploit. We've put in the padding now, and now the return address for win. Let's go ahead and build this again. ROP vuln, set the same breakpoints that we had. Let's go ahead and put one here, and then let's also put one right here. Okay, and now let's go ahead and run with our new payload. And now this should be stopping right before we do our read input, so everything should be fine. And now let's go ahead and continue. Let's check in on what our input's going to look like. Let's do, let's do 4 words this time so we can get all 4 of the entries that we're looking at. x/4gx RVP minus 16. And okay, now you can see we've filled in the padding here, and then this slot for the return address has successfully been overridden by the address of win. So if we continue execution again, we should see that winning message get printed out. And there we go. We got you won in our terminal. We successfully directed execution to the win function by overriding the return address there. And yeah, we just completed our very first buffer overflow attack. So hopefully you guys were able to follow along with that. If not, I mean, feel free to go back through it slower, try to learn all the GUI commands and stuff. On my repo, I've included resources so you can learn more about that. But yeah, hopefully this was informative and have fun. Thanks.